So, my name is Sean Ernst, and I'm here today to give you all my dissertation defense. This is the work that I've been chugging through for the last probably about a year and a half now, and I'm really excited to share it with you all. So without further ado, why don't we get started and hit the button that is supposed to work, but it's not working, so we'll just hit this. It always works. Oh, now it's not working here too. That's exciting. Is that because we're not on the window? That is because we're not on the window. There we go. Now we are. Everything works. That's handy dandy. So to start, for my master's work, I looked at the convective outlook from the Storm Prediction Center. It's a product that forecasts the likelihood or the significance of potential severe weather across the lower 48 every day, multiple times. This particular forecast is from May 20th, 2019, and it's a lovely display of all the different categories you can have, all the way from marginal and slight in New England to enhanced, moderate, and high in Oklahoma. We're not going to talk about those anymore today. I've talked about that more than enough with my master's work. Today, instead, we're going to look at the probabilities that underlie this categorical forecast. Specifically on this day for tornadoes, we can see that across Oklahoma in that high risk area, there is indeed a very high risk of tornadoes, up to 45% across western Oklahoma. That goes down but up to 30%, 15%, 10%, et cetera, as you get away from where the forecasters think the most likely place for tornadoes is going to be. We also have a 2% risk of tornadoes within 25 miles of a point across New England. Now, there's a very different level of probability here that we're seeing for tornadoes, but having grown up in New England, and anybody watching who's from the New England area is probably going to know that a 2% is not something you see every day up there. It's also true that a 45% is not something you see every day in Oklahoma. But when we ask people to interpret this product, this probabilistic product, we get a lot of interesting questions. Like people will ask, how often do we get this level of risk here? Or some people say that, 15% doesn't mean very much to me, 15% chance of rain, I'm not even bringing a rain jacket to work. But knowing this happens once a year does. Or just in general, what is the context of the risk that you're showing me? Other research has shown that there is a desire for context, even with groups like emergency managers. So we see that emergency managers have been seeking place-attached meaning in these Outlook products. They want to know how the forecast compares to both local climatology and local vulnerabilities. And we've also seen that odds ratios, which are a way of comparing the likelihood in the forecast to the climatology behind the scenes, do a better job of encouraging precautionary action for low probability events than yes or no deterministic or probabilistic forecasts. So we here at IPRA have come up with something truly innovative, something groundbreaking, something that's going to take everything you know about risk communication and split it in half. What is this incredible innovation that we've developed? Well, it's a new math technique that we call division. It's never been used before. We definitely innovated it at IPRA. Joe can back me up on this, probably Kenzie too, although she might be like, no. It's definitely new. But jokes aside, we actually do use division to create a new risk value that could potentially help communicate these rare event risks. This is something that is called relative risk. The way we calculate it is we start with that SPC probabilistic forecast. That's the top of that division equation we have going on there. This is that, again, that 20th of May 2019 forecast absolute tornado risk. The second step is to take the climatology, which is the background likelihood of a tornado on average across the US on that day. And we divide that absolute risk by that climatology. Ouch. Then you get, as a result, a relative risk value, which you can see for this forecast on this day, we've got a 50 to 100 times more likely than normal to see a tornado within 25 miles of a point across western Oklahoma, where we had that 45% risk. But we see that equal value also showing up in Maine, where we had that 2% tornado risk, because tornadoes are not nearly as common when you get up into that part of Maine, partly because no one lives there, partly because you don't see as many tornadoes the further north you go. So this is a product that has been suggested by Murphy as far back as 1991 as a means to potentially help communicate rare risks like tornadoes. So We've solved the problem. We're done. My dissertation has finished. You can now judge me. I told you it would be under 45 minutes, and we've successfully done that. This is how we do things. We create a product and we just put it out there into the world and we're good. Nothing ever goes wrong for sure, no doubt. That's not quite the case. And that's a perfect time to get an email. When in the past, we have sort of focused on the production side of developing new forecast products and a lot less on the reception side of how people are going to receive, interpret, and respond to the new information that we're producing. And that can be problematic because if you put information out there that's going to freak people out, or it's going to make them underestimate the risk at hand, there could be serious potential consequences for that. So lately, things have been getting a lot better. There's been a lot more integration of social science and meteorology research. The Facets or Forecasting a Continuum of Environmental Threats initiative has from day one tried to incorporate social science into every step of the forecast process, all the way from developing the forecast to looking at how people respond to that information and how we build back better for the next storm. Vortex Southeast and Vortex USA have also started putting a lot more money towards social science investigation and trying to figure out how people are interpreting tornado warning forecasts and things like that. And of course, we also have graduate studies that have worked to try and build in this understanding that developing a product also involves looking at how people respond to it. In particular, we have Kenzie Krochak's 2020 dissertation and Dr. Kim Cloko-McLean's 2013 dissertation that did just this. So the question is, for me, how are we going to rigorously test relative risk forecast products and get a better idea of whether or not these are going to help users produce value making decisions using this information? The first step is to look at the climatology. How does relative risk vary across different tornado events? Because we need to get an idea of what kind of numbers this thing is going to be spitting out before we put it in front of people. Second, we need to look at how this product might be communicated. And right now, the #1 communicators remain TV meteorologists, both on TV and social media. This is how weather service products are most often reaching members of the public. So how are these intermediaries going to repackage that information? And then third, comprehension. How does the public interpret this information? How does it change their perceptions of how concerned they'd be or how likely to respond they might be given a severe weather forecast that includes relative risk? So without further ado, let's get started on that climatology. This is that weather sort of part, that production part of this product. So first of all, what is the climatology? What is the forest of relative risks for tornadoes across the US? What do we see in this area? What are the different areas of different trees? What are we kind of looking for when we look at relative risk? I see Harold's already got his head in his hands, so we're deep in metaphor land here. This is good. Next, how do relative risks compare to practically perfect absolute risks across tornado events? Now, I say practically perfect because SPC has only been forecasting the probabilistic likelihood of tornadoes since 2001. So if you want to look at lots of really fun past events like April 3rd, 1974, you can't use the forecast. You have to look at what a perfect forecast would be if we looked at the tornado reports and then applied a smoother on those. So we'll be using those for this chunk of the presentation. And then finally, what impacts might understanding this climatology have on the relative risks that will be communicated? Basically, how are we going to tell people where the really big trees in this forest are? So for methodology for this section, we first need to calculate relative risks for a large body of climatological data. And to do that, we use the methodology from Brooks et al. 2003 that was also used in Krochak and Brooks 2018. To do this, we create a daily 12Z to 12Z, that's Greenwich time for those of you who aren't familiar with meteorology terminology, a daily climatology of 1950 to 2021 EF1 or greater tornado start points. We use EF1 or greater tornadoes because the record keeping for EF0s can get a little weird depending on what part of the country you're in. So you've got more consistent data for these more damaging tornadoes. And we use the start point data just because most tornadoes do not have a long track, and those that do are usually not going to cross too many of the grid squares that we're going to be showing next. We take that start point data and we applied it to an 80 kilometer, which is a roughly 25-mile grid that is masked to the US. We mask it to the US because we don't have data from outside the US. So you don't want to see like 0.00001% chance of a tornado somewhere in Canada that's going to mess with our data set. So we chop all that data off. We use that 80-kilometer grid because we're comparing to the SPC forecast, which is a probabilistic forecast for tornadoes within 25 miles of a point. We then apply those tornado reports to the grid. So if any tornadoes occur within a grid square, or the start points occur within the grid square, that grid square gets a value of 1. So you can have multiple tornadoes in one grid square, but your grid square value is still going to be 1 because a tornado has occurred within 25 miles of you. We then use a Gaussian smoother, which we used a value of 1.5 for the spatial smoothing parameter, which translates to roughly 120 kilometers, and a 15-day on either side temporal smoother. What that does is that takes those values of 1 grid squares, not GWID squares, and flattens them out so that we have a lower probability value, and that we also account for the variability across time. So for this day, which is April 27, 2011, you notice there's some probabilities that increase in North Carolina as well as Arkansas. That's because there were tornado outbreaks on the days surrounding that April 27th event. And that's why these are showing up when we've smoothed our data temporally. Finally, we take all those temporally smoothed days across that 1950 to 2021 data set. We find the mean and then spit that out on this lovely little graphic here. And this is our climatology that we use for every single day of the year. We have 366 days because we include leap year days, so February 29th, and then use this to calculate our relative risks. So we already went through this, so I'll go through it pretty quick, but we start with the practically perfect timecast for those EF1 or greater tornado reports. We're using that instead of the forecast absolute risk again, because we don't have that data before 2001. And we again use that 1.5 or 120 kilometer spatial Gaussian smoother and then crop the smoothing to a 2% risk. And the reason for this is because the SPC does not issue forecasts below 2%. So we're not including below 2% in our practically perfect forecast. We then again take that value divided by the climatology and we get a relative risk. Note that this is again for that 20th of May 2019 that we started the presentation with, and note that we're much lower relative risk when we're looking at the practically perfect, because that is based off of what actually happened, and there were fewer tornadoes on this day than the forecast expected. So that's just a discrepancy to keep in mind. Practically perfect is not the same as a forecast. So when we look at all the data points across every single day in the database, which is a number that is frighteningly large, we can plot that out on this graphic here and get an idea of what all these relative risk pairs look like. So we have relative risks on a logarithmic scale on the x-axis and absolute risks on a normal scale on the y-axis. So when we look at this data, we can see that the majority of relative risk events occur when you have a relative risk of less than 1,000 times or 100 times more likely than normal. I use that X as a sort of subscript for times more likely than normal. And then a less than 10% risk. So in the lower left corner of this plot here. So most of these are sort of low end events, which doesn't surprise us because severe weather generally isn't occurring in a big way. But you may notice that there are a lot of these outliers, and those are going to be your big time major severe weather outbreaks. For example, at a 65% absolute risk and a little bit over 150 times more likely than normal, we have April 27th, 2011 in Jackson, Mississippi. We also have over here a much higher relative risk, but a comparable absolute risk, the December 15th, 2021 event in Omaha, Nebraska, which was a very much off-season event and thus has a much higher relative risk, even though the practically perfect absolute risk of tornadoes was very similar. Note, however, that there's a lot of extreme relative risk cases. You see all these little purple boxes up here. That means that there's just one event or one grid space where you had that pairing of values. Down here, we're getting some of those yellower colors, which are getting into a higher number of cases. So we're seeing a lot of extreme relative risk values greater than 1,000 times more likely than normal, even though the absolute risk is still less than 10%. So what's going on there? The answer is the extreme rarity of tornadoes in the western US, as well as a little bit from the extreme rarity of tornadoes when we get into New England and the northern plains in the wintertime. So these events, we're getting in the hatched areas, relative risks as high as 2,000 times more likely than normal, which is fairly large and may have some impacts if we're trying to tell people that what their tornado risk is. And again, remember, this is happening at low absolute risks. This is a ranking of the top 10 relative risk events in the database from 1950 to 2021. And you can see that the number one day has a relative risk of 2,697 times more likely than normal for an absolute risk of 2.33%, which is, for all intents and purposes, a 2% tornado risk. And a single tornado occurred, just one. Where was it? New Mexico, northern New Mexico, the day after Christmas, which is both a place and a time you probably would be shocked to hear a tornado occurred. And that's why we get that massive relative risk, because the climatology at this point is basically this tornado. So if we cut off the continental divide and we only look at relative risk grid points that are east of 105 west latitude, we get a very different result. We now see that the number one event was December 15th, 2021, which had an absolute risk value of 18.78% at the point where a 2,600 times more likely than normal relative risk occurred. This was an extreme tornado outbreak far north of where tornadoes usually occur, up in Iowa and Minnesota at this time of year. And so it makes more sense that we see this value. But we're still seeing that there's a lot of single values when we get into the tornado count for some of these top 10 events. So we're still seeing that a lot of high relative risk events occur when a single tornado occurs in a place and time you don't expect. So we can also learn a little bit by comparing the two distributions and looking at percentile rankings. So we can get an idea of how often each of these absolute risk values, and then compare that to how often relative risk values occur. So for example, we'll try that 30% absolute risk. We can see that it is at the 98.88 percentile, which means if we look at that distribution there, 98.88% of absolute risk values in the database are less than a 30% absolute risk. And then of course, 1.22% are greater than that. We can also look at the point where 1.22% of relative risks are greater than that value, and that turns out to be right around 287 times more likely than normal, which means we can start to compare these absolute risks in terms of their frequency of occurrence to different relative risks. So 2% occurs about as often as 5 times more likely than normal relative risk, 10% 50, 30% 250, 60% 2,000, which makes sense because the SPC has only ever issued a 60% chance of a tornado within 25 miles once. So some potential use cases now that we understand our data set a little bit better. The case that inspired me to look at relative risks and got me really excited about the potential was June 1st, 2011, which featured a long track EF3 tornado in southern Massachusetts. Note that when we look at that practically perfect, based on where those tornado reports are, the little black triangles, we've got 2 areas of a 10% chance of a tornado within 25 miles. But when we look at the climatology, we see that our climatological likelihood of a tornado up into Maine and then across southern New England is in the 0.05 to 0.1% chance of a tornado within 25 miles, which is very low. So that means that we get some pretty large values of relative risk out of this practically perfect absolute risk. You can see where the EF3 tornado occurred, we have an over 100 times more likely than average relative risk for that area in this time of year. It gets even higher into the 250 times more likely range when we get into Maine, where again, we have our lowest climatological values for tornado likelihood. We're looking at the 17th of November, 2013. We have another event that might help people that are caught off guard better understand their tornado risk. This event had a very significant number of tornadoes and a widespread 45% chance of a tornado within 25 miles, which, given the climatology being similar to that of New England in June, leads to a widespread relative risk of 250 times more likely than normal. This might help people in the area understand that, you know what, you're in Tornado Alley, you get these things in the springtime. This isn't springtime. You're not used to this. This is not going to be something you're used to in November. Be ready to anticipate something out of the ordinary. And then finally, we can look at that fun date that I mentioned earlier, which is April 3rd, 1974. This is considered one of the two super outbreaks in American history, where you can see a very broad 60% contour for that practically perfect exists across the Ohio Valley. We have a little bit higher climatology at this time of year. Now we're starting to get closer to those 0.4, 0.5% risk of a tornado within 25 miles. But because the practically perfect is that absolute risk is just so high, we can already see there's a 250 times more likely bubble across areas of eastern Kentucky and into West Virginia, as well as this broad 100 times more likely than normal risk that is capturing most of the tornadoes that occurred on this day. So we saw these events where there's something really out of the ordinary, and that might be a place where relative risk can be useful to communicate the tornado threat. There are some places where this may not be quite how things work. So I'll bring back up again that 26th of December, 1966. Do we need to tell people in Santa Fe that their risk of tornadoes today is 2,600 times more likely than normal for the chance of maybe a single tornado? I don't know. That's a potential challenge that this data set is revealing to us. Another potential challenge is when we look at another super outbreak, the other super outbreak, which is the 27th of April, 2011. Now we see that most of the tornadoes were concentrated in the deep south, but there were tornadoes all the way up into New York State, which led to a 15% absolute risk up there. But when we look at the climatology, it rapidly decreases as you go north, which means in the deep south, we end up with a relative risk that's around 100 times more likely than normal, which for that area in late April should probably ring some alarm bells because you're already expecting tornadoes. But if we show people this graphic, are they going to start looking at these peaks of relative risk that are much further to the north and start thinking that, oh, the worst danger is going to be north of me. It's not going to be where I am, even though that absolute risk is showing us that the peak of the tornado threat is going to be across the deep south. And then finally, we can look at a day like the 20th of May, 2013, where we, of course, had a deadly EF5 tornado just a few miles north of here. On this day, we get that 15% absolute risk in the practically perfect hindcast because of the tornadoes that occurred. But because we're at peak climatology for tornadoes, we're almost at a 1% chance of a tornado within 25 miles of a point in late May and in central Oklahoma, we end up with a relative risk that's just over 5 times more likely than normal. I'm not sure this is how you want to communicate a potential high-end tornado threat to central Oklahomans by saying, you're 5 times more likely than normal in late May to see a tornado today. It's just another day in May, when it's really not another day in May. So to conclude this section, relative risks are best for areas with an established tornado climatology, or at least that's what we're seeing in the data and assuming. And we see that areas and times with few recorded tornadoes see extremely high relative risk values that may not be useful to communicate. So we want that established climatology if we're going to be presenting these relative risks to people. It may not be useful when we get west of 105 west. Relative risk may also add most communication value in those off-region, like in New England, or off-season, like in November, tornado events. However, there's also some important questions that we need to answer. The relative risk does not appear to be useful to communicate these average tornado events, kind of like May 20th, where an average spread of tornadoes is expected in a time of year where tornadoes are also just generally expected. We also see that there's this north-south variation in relative risk because of how climatology changes when you move towards the north, and that could cause some problems with bias when we look at those visuals. And then finally, how do users interpret the very high values of relative risk we're seeing? We're seeing values of 500 times more likely than normal on a fairly regular basis. How are people going to react when we tell them that they're 500 times more likely than normal to see a tornado today? In other words, relative risk appears to work 60% of the time, every time. So it's good to know. When we look at the second part of this talk, the communication, how is relative risk information going to be of value to broadcasters? How might they present this relative risk information to their viewers? And of course, what concerns do these broadcasters have with presenting relative risk information? These are all important questions to answer before this kind of product gets shipped out to the public. To answer these questions, we designed a study where we used a series of focus groups involving 12 broadcast meteorologists from across the US, although mostly east of the Rockies. across 4 interview sessions with a snowball sample that the KFE TV team helped us collect. I really have to have a big thank you to Dr. Cody Berry for helping me get out and reach out to these broadcasters so that we could perform these focus groups with them. To interview during these focus groups, we have a couple meteorologists there. We did it online through Zoom. We first asked the broadcasters to identify their familiarity with the current SPC outlook probabilities. We then presented this incredible little viewer that Joe helped build that presents experimental relative risk plots right next to absolute risk plots. Broadcasters were able to zoom in on these and check things out, and it was a really nice interactive way for them to kind of hone in on areas they might be interested in to understand the relative risk in those places. If you, dear audience, want to look at these, I have a handy dandy QR code here that you can use. Just keep in mind, if we all log on to it at the same time, it's definitely going to explode. So it might be the kind of thing where you save it and look at it later. In any case, after showing the broadcasters these experimental plots, we asked them about what potential value and uses they saw for these relative risk plots. And we sort of pushed them a little to try and imagine a situation that even if they didn't feel like they wanted to present it, when would they be most likely to present it? Just so we could get a better idea of what conditions might be most useful to present relative risks. So to analyze this data, because we have qualitative data here instead of quantitative, we use something called thematic coding, which is a method for identifying, analyzing, and reporting patterns or themes in a data set. It's a multi-step process that basically amounts to using a lot of post-it notes to sort of like, if broadcasters mention, oh, I'm not so sure about showing probability to the public, you might say that's a PRO code. And then you put that down there, you pull all those coded lines out, put them together, see if there's any themes there, eat some ice cream, and then look back at your themes and compare them to the data to make sure that they line up with what the qualitative data is showing us. The product of this analysis is something called a thematic map, which branches out from a global theme into organizing and basic themes that describe the overall message of what the interviewees were trying to tell us. Without further ado, here is that thematic map. We start in the center with broadcaster relative risk perceptions and break out into concerns, usage, and how broadcasters would present this product. For starters, 10 of our 12 broadcasters said that they felt that the numbers, just in general, not just for relative risk, can be very misleading to their audience. You know, if you tell your public that there's a 10% chance of rain, I'm not actually going to get rained on, so that could actually hurt your message if you're saying there's a 10% chance of tornadoes. Broadcasters feel that those absolute risks are a little bit low to show to their viewers. But then they think that it would probably take a lot of education to show their viewers something new like relative risk. 6 broadcasters mentioned that they're not sure they'd have the time in their 3-minute shows to educate viewers on how to interpret these new probabilistic values. Further, relative risk was seen, opposite to those absolute risks, to blow things out of proportion. This is my favorite little quote here. This broadcaster says, you know, you show someone 250 times more likely than normal, they're going to think they're in the Twister movie that afternoon. So they're very concerned that these are going to overhype the potential for tornadoes for a given event. But there also were a few broadcasters that felt that the relative risks actually downplay the risk of tornadoes. For example, looking at the April 27th map, and they wonder if it will diminish the significance of some of those extreme events that occur during a time of year where you already expect tornadoes. Finally, for the concerns, 7 broadcasters mentioned that it distracts from the most likely location of a tornado. They highlighted in particular this day, which is the December 10th, 2021 event, and noted that, again, similar to that April 27th event, the highest relative risks are offset from the highest absolute risks. And so they worry that showing their viewers this map might lead them to think that the threat or highest threat is going to be in a different location than the absolute risks, which are showing where the absolute highest risk is. When we get into usage, those concerns about how much education it's going to take and how the numbers are misleading leads the broadcasters in these interviews to think that the relative risks are going to be good for them, but not so good for the public. They do note that there's probably some behind the scenes uses, such as figuring out staffing and knowing if they need to call in extra hands to make sure that there's enough people to cover the event. And they also feel that the relative risks are beneficial to help them know that an event is unusual, that according to climatology, it's 50, 100, 200 times more likely than normal. When it comes to presenting relative risks, We see the broadcasters felt that they can use the product to show viewers, here's why this event is different today. They can say that the risk today is X times higher, the risk in this location is X times higher than in that location. It helps them point out potentially to viewers that their risk is not normal for this day. When we pressed broadcasters and asked them to sort of say when they would be showing this product, they were a bit split again, but most broadcasters, 7, suggested that off-season, off-region events would be the best time to present relative risk information to their viewers, while 3 broadcasters were more feeling that those in-season, in-region events were better because you don't get those overinflated relative risk values. Potentially due to that concern about how the map works and how it might distract from the most likely location of a tornado, 3 broadcasters said that they don't really want to show the map. They think it's misleading. They might talk about it, but they're not going to show it to their viewers. On the other hand, 8 broadcasters said that they really like the map. So again, we're seeing a lot of sort of give and take here. It's a very personal experience how you might use relative risk. And those broadcasters were saying they might use it in certain circumstances on the air or on social media in particular to get people to pay attention to things. So it sort of might be useful as an eye grabber, get that attention, get people thinking about their tornado risk. And then finally, some broadcasters, which goes against everything that I found in my master's work, really thought that the relative risks would be great if you standardized it to a 1 to 5 scale instead of presenting any probabilities whatsoever because numbers are bad. Those broadcasters said, though, that there is some reasonable things that are being said here. In fact, that putting everything in one lump sum helps them be more efficient in their process of knowing what their risk is and what decisions they need to make. So there could be some value into potentially working relative risk into the pre-existing convective outlook, that's that high, moderate risk kind of product, so that they can just, it's like McDonald's, it's fast food for meteorology. So here's one last look at that full thematic map. So, you can take the pictures last longer, very nice, very pretty, I worked hard on it. But anyway, talking about our results for this section, there's a general suspicion amongst broadcasters, at least the ones we interviewed, of the public's ability to interpret probability information. They see the absolute risks as too small and the relative risks as too large. You're in the Twister movie now. There's also a bit of concern over the split between absolute and relative risk maxima, confusing people. Broadcasters also see value for relative risk for their own use, not so much for the public. And when pressed, they say that they're most likely to present the product in a map format for off-season, off-region tornado events. They also might prefer to integrate the product with the categorical outlook, just as a one-stop shop. For my meme for this part, we see me, a social scientist, saying that broadcasters, it's time to look inward, ask yourself the big questions. If probabilities are good for you, why are they bad for other people? It's a worthwhile question, and it might be a little bit of bias there, but that's outside the scope of this project. For the final section, comprehension, let's look at the general public. What happens when you tell someone indeed that there's a 250 times more likely chance of a tornado? Is that the Twister effect? I don't know. So we start out here with how does relative risk impact public perception of tornado risk? How does telling people these probabilistic numbers change the way that they're going to interact with their environment and change their day, or maybe even take shelter already from tornado threats? Who wants to learn about relative risks today? Second, is the interpretation of relative risk impacted by anchoring effects, which are when you see a big number followed by a little number and you're asked to report some number, you're more likely to say a bigger number because your mind has sort of gotten stuck on that big number that you saw first. We'll see a better example of this later in the presentation when we look at the data. Third, do increasingly large values of relative risk affect risk perception? We know people are awful at thinking about large numbers. I can tell you that Keurig built 18 billion pods last year. That's a big number. You say, wow, that's a lot of Keurig pods. When I tell you that that takes up a space that is 349 feet by 870 feet by 240 feet, now you go, wow, that's a really big number. It's really hard to conceptualize these massive numbers when, what's the difference between 17 billion and 18 billion? It's hard to say. So what's the difference between 500 times more likely than normal and 600 times more likely than normal to see a tornado? There might be some issues there. This is that living in twister effect that we're talking about with the broadcasters. And then fourth, do false alarms with relative risk forecasts impact forecast trust? It's a really hot ticket item right now. If you go to any presentation, I remember after presenting some of this work at SLS last year, one of the big questions was, what happens with the false alarm effect? What about how people are going to react when you get a big number and nothing happens? You know, how is this going to reduce trust in the weather service? It's worth looking into that. So for data for this section, we used the IFRA 2021 and 2022 Severe Weather and Society surveys, which are a representative sample of the US public. We sample a panel of potential participants that are collected by a third-party company. And that third-party company tries to select participants based on the demographic information we have from the US Census. So we're basically trying to create a little miniature version of the US population. These particular surveys had 1,550 and 1,409 respondents and occurred in the summer of 2021 and 2022. You can kind of get a general idea of how spread out across the US our participants are by looking at these two plots here. So to answer those questions that we just asked, we need to put some questions into the survey. And the first one that we put in the 2021 survey, we asked participants to imagine being at a Saturday, it's a Saturday morning at 8 a.m. and you get this forecast. It says different morning because there's a lot of questions in these surveys. But what we do from there is after telling people that it's a Saturday morning, we split them into one of 6 groups. The first group sees that there's a 2% chance of tornadoes today. That's the current system. The second group sees only that relative risk. Tornadoes are 20 times more likely today than on an average day like today. The third group sees only both pieces of information combined. So a 2% chance of tornadoes is 20 times more likely than normal. Now there's only 3 groups on the screen here. I said there were 6. The reason is because we also gave them a higher risk scenario where participants were only shown 5% chance, 50 times more likely today, or both pieces of information. After seeing just one of these 6 pieces of information, note that there were no maps shown, just as text, we gave participants a pair of questions, asking them to rank from 0 to 100, from not at all concerned to extremely concerned, and not at all likely to extremely likely, how concerned they were on getting this forecast, and how likely they were to change their plans for the day if they received this forecast. We can think of this as concern and likelihood of response. So when we look at this data, we get this big complicated plot that I'm now going to break down really quick so it's really easy to understand. We have the low risk and the high risk groups on the left and right. You can see that now there's 6 groups divided along that x-axis. And then we have the concern and likelihood of response answers on the rows. So basically, if we're looking at this upper left, we're looking at the low risk group for their level of concern. And when we look at that particular group, we see that for the absolute risk group versus the relative risk group, there is a 33-point increase in their level of concern, all the way up from a little bit over 20 to near 60, which on a 100-point scale is wild. That is a third of our scale that people have jumped up in concern. That is a huge shift. And it's way outside these 90% confidence intervals that I plotted around the average response for each group. But when we look at the combined format, level of concern is increased, but not nearly so to such an extreme level. It's increased by about 4 points in that the low risk group and by about 11 points in the high risk group. Again, all of these differences are statistically significant because we can see that the central tendency values are outside of those confidence intervals, at least at the 90% confidence level. When we look at the response values, it's basically the same story. Huge increase in likelihood of response for just the relative risk, smaller but notable increase for the combined information. So we're not going to talk too much about response because it's so similar to concern. Now, the interesting thing in this data is when we compare across the 2 risk levels. So now the vertical is our different conditions, the absolute, relative, and combined groups. And then the x-axis is splitting our groups up by which risk level they saw. And if we look at just the absolute risk group, there's a 2-point increase in their concern. For the relative risk group, there's a 1.7-point increase in their concern. Basically, their concern between the low and high risk conditions is not changed. It's basically the same. But for the combined group, we see an almost 10-point increase in concern between the lower risk and higher risk group. So what this suggests is that when you combine absolute and relative risk information, you're helping people discern between different levels of risk a little bit more effectively. Second, to look for that anchoring bias, as well as the effect of large values of relative risk, we asked a question in the 2022 survey. Again, we love our Saturday mornings at 8 a.m. Personally, I'm asleep, so very different answers for me. But we have 10 groups this time. The first 5 groups were shown relative risk information first, which is a larger value of either 20, 50, 100, 200, or 500. Followed by the absolute risk information, which is a 15% chance of tornadoes in your area today. It was 15% for all the groups that saw this information. The second group of 5 saw the absolute risk first, which again is a smaller number than all of the relative risk values. After seeing this information, we asked our participants those same 0 to 100 scale questions, and then asked participants to rank how reasonable they felt that the forecast was. Because if we get a 500 times more likely than normal risk, and people think that is completely unreasonable, that's going to tell us something about that large numbers effect, that sort of living in twister effect that the broadcasters were worried about. When we look for an anchoring effect by splitting up our participants by whether they saw the absolute information first or the relative information first, we do see that there is a statistically significant difference across these different concern and responses. So people who are seeing the relative risk first, the larger number, are ranking their likelihood of response and their level of concern higher. They're associating larger values with their, because they've seen that larger value first. This may be an effect of the fact that we're asking them to numerically rank their concern and response. So it might change if we used something like a Likert scale, where we ask them that their concern is very low all the way to very high. But it is interesting to see that this kind of effect is occurring with just the change of the ordering of what information is presented first in a sentence. However, there's not a really significant change that we see in the reasonableness of the forecast. And in fact, much to my happiness, it's above 50%. So people are like, yeah, this isn't too bad. This is reasonable. I can see this. So not too much of an anchoring effect when it comes to the reasonableness of the forecast. When we break things down by which value of relative risk we see, kind of surprisingly, there's really not a significant change in the variables across the different levels of relative risk. Remember, the absolute risk is staying the same. The only major visible increase in concern occurs for the 500 times more likely than normal group, and it's still not statistically significant. It's within the confidence interval of that first value, the 20 times more likely than normal group. So not really seeing much change in level of concern or likelihood of response when we increase these relative risk values in this combined format. But again, the forecasts were seen as consistently reasonable across all levels, and they're again above that sort of half and half sitting on the fence value. So people seem to think that this isn't an unreasonable forecast to receive, even all the way up to that 500 times more likely than normal level. For the final bit of the survey, we basically set up a false alarm scenario where forecasters are underestimating or overestimating forecasts. Errors happen, we know this. And so we asked them again to put themselves in that Saturday morning. We showed them the same forecast that they saw for that previous one, so that combined format, and then asked them that, the day progresses, imagine you see some rain and lightning, but there's no tornado within 25 miles of you. Would this influence your trust in future forecasts? No, not really at all. Over 60% of respondents for each of the different relative risk levels said that that a false alarm forecast would have no effect on their trust in future forecasts. And in fact, if you notice, these are almost all just very, very sharp, but normal distributions where we have a relatively equal number of participants saying that it would reduce their trust or increase their trust. So the net effect that we're seeing here is basically nil. There's not really an impact of trust from this scenario that we presented to our participants. So, looking at public comprehension of relative risks, we see that absolute risks lead to a lower level of concern and response, and relative risks lead to a higher level of concern and response. With that combined format, seeing an interesting differentiation in concern across different levels of risk, at least at those lower end risks that we showed. There's also appears to be an anchoring effect when you combine the risk presentation format. So if you're putting those relative risks first, You might see a little bit higher level of concern or response from your people who are viewing that message. And also the concern and response does not seem to have a significant change across increasingly large relative risk values. But there's also not a significant loss or gain in trust after a false alarm for a combined risk forecast, even if that forecast involves a relative risk of like 500 times more likely than normal, which is not what we really expected to see. In other words, that's the broadcasters telling me that members of the public don't understand probabilities, and here's me pulling up the third part of my dissertation to say, let's hold up on that and maybe look at the data first. So, to wrap things up, the big picture view, what did we learn from the three components of this investigation? First, from the climatology, we saw that these relative risks are likely most valuable where tornado climatology is strong and pre-existing. We have some tornadoes there. And also for those off-season and region events, but maybe less so for those average events. For communication, we saw the broadcasters suspect the public's ability to interpret probability, but relative risk is of interest for their own personal use. Finally, for the comprehension section, we saw that the public thinks, or the relative risks appear to be best used in tandem with absolute risk because by themselves, they way overinflate concern and likelihood of response. But there's no clear negative effect of high values of relative risk on concern or trust. So overall, this tells us that, you show a Cleveland County resident in 2023 that you're 100 times more likely than normal today to see a tornado. They're probably just going to tell you, I like those odds, although my friends would say that we're not allowed to talk about odds anymore after we may have talked about odds before someone's house got hit by a tornado. we live and learn. We live and learn here. But relative risk might be best used as a supplement to absolute risk, not a replacement, to highlight unusual tornado events. It does need further study. It could be useful with different hazards like tropical storm winds. As well as in locations where hazards are basically unprecedented, like those areas west of 105 West, the Continental Divide. Is relative risk even worth saying anything about or even calculating in the Rockies just because there's no climatology? That's a good question that still needs to be answered. In any case, we've got a few references that I mentioned in this talk, but before we wrap up here, I really want to acknowledge all the people that made my ability to talk at you for well over the 45 minutes I said I would talk possible. My advisors and mentors, I can't say enough about. My committee for being here and supporting me through this journey is huge. All the teachers throughout my life that have instilled the love of learning and the want to sort of better myself through knowledge. My friends who have kept me sane and also made the good times even better. My family for always telling me to do what I felt like I should do with my life. And now I'm right there doing it. And of course, everyone here viewing this presentation, thank you for being here. It means a lot. And with that, we have now actually explored the problem. So now I can say that my dissertation defense is done and I'm ready to receive your questions. Thank you all very much.